Good morning. All right. So, yesterday we went through the practice test. So just keep in mind that is due Tuesday by night. So just make sure you get that done, sometime over the weekend or Monday, so that you can get that submitted on Tuesday. Let me know if you have any questions about the test in general, or especially if you're trying to upload it, have any issues or anything like that. Let me know if you're having any issues there. We are going to move on to section 4.1 today, which is exponential functions. So I believe those slides have been posted. Let me double check that right now while I'm thinking about it. Just make sure they're there. And if not, I will make them available. Okay, they are there now. Okay, so if you didn't have access to them earlier, they should be available now. All right. Any questions, comments, concerns about anything right now before we get started today? All right. So we are going to start looking at exponential functions. And so this is going to be a key component of this unit is going to be about exponential functions. And then the other half will be what we call logarithmic functions, right? So those are kind of the two big things we're going to talk about in this unit. Then we'll do some application problems with those two types of functions towards the end. But that'll be everything that's on this upcoming test for this entire unit. Okay, so definition of this should be exponential functions here. Sorry. Copy this from another slide. Okay, so this is the definition of an exponential function. So an exponential function with a base a is defined for all real numbers x, okay, by this function here. So this a is going to represent some real number, and the x is going to be variable. So we're raising some number to the x power. Right? So that's the key: is the x has to be in the exponent, and the base is going to be some real number. Here it's saying that a needs to be greater than 0, so all of our exponential functions that we look at, we're just going to assume that the base is greater than 0, it's positive, and then if there happens to be a negative or anything there, that's when we're going to start using those transformations that we looked at a couple of units back. Okay, so just keep in mind here, we're always assuming the base is positive, and then if there is a negative there, then that's just going to transform the graph. And in this case, a can't be equal to 1 because 1 to any power is just going to be equal to 1. So this would just give us a horizontal line if a was equal to 1, right? So that's why we can't have 1 as the base, and we want to use a positive number as the base, but this is going to be the general form for an exponential function. Okay? All right, so this function here, f of x equals 3 to the x, this is an example of an exponential function because we have the base as a number, we have x in our exponent. So now we want to actually calculate each of these values right here. Give you a chance to write that down. All right, so if we look at the first one here, if we want to find f of 5 and our function is 3 to the x, what are we going to do here to calculate f of 5? Good, so we're just going to do 3 to the 5th power, right? Because the 5 now goes in place of the x, that's in the exponent, so this becomes 3 to the 5th. So what are we going to get if we do 3 to the 5th power? Good. So this should become 243. Now, if you're looking for how to actually put this into your calculator, all the graphing calculators and a lot of the scientific calculators, they use what's called the caret to do exponents. So we would put this in there, we'd put our base first, then we would select the caret key, which is a little housetop looking thing, and then we're going to put the exponent. And so when you're putting it into the calculator now, it's going to be 3 to the 5th power. And when we do that, it should give us this value here. And you can use that same notation even if you're just using like a Google calculator or something like that. The calculator on your phone usually would have like an actual exponent key. So just let me know if you're struggling with finding a way to put in exponents there. Any questions on that one? so now the next one, what are we going to do here? Good. Now, when we do this, we want to make sure that the entire negative 2/3 is in the exponent. So just make sure when you put it into your calculator, sometimes you might have to actually do parentheses around the negative 2 divided 3 just to make sure that it's taking all of that stuff into the exponent here. Okay, now, if you have a calculator where it actually gives you the little box in the exponent, then you should be fine just putting in negative 2/3 there. But otherwise, if it gives you this string of numbers like this, just make sure you group the fraction together. Now, if we do 3 to the negative 2/3 power, we'll round that to 4 decimal places. What should that give us? Good. Okay, so 0.4807 if we round that one off. Okay. Any questions on that one now? All right. What about our next one then? So what are we doing this time? Good. So it's going to be 3 to the pi power. And if you have a pi key on your calculator, actually use the key just so it gives you a more representative answer here rather than just doing 3.14. We can just do 3 to the pi. Again, we'll just round that to 4 decimal places. Okay, so 31.5443 looks good. Okay. Any questions on that one? All right, and then our last one here, again, we're just taking this value, we're putting it in our exponent. This is going to be 3 to the square root of 2 power. Again, we'll just go 4 decimal places on this one also. Good. So 4.728 looks good. Any questions on how to put any of those into the calculator now? All right. Now, this slide, we're actually going to try to sketch the graph of these functions, right? So our first one is 3 to the x, that same function we were just looking at. Now we're going to try to think about what that graph would look like. All right, so if we don't know what a graph looks like, right, and let's just assume right now we don't have access to a graphing calculator or Desmos or anything like that, what could we do here to help us figure out what this graph is going to look like? Good, right? So we can create a table of values. We can just plug in some numbers and we can see what values we get, right? So that's what I'm going to do here. So I'm going to create a table, X and Y. And so now we just need to choose some X values that we're going to plug in there, right? So what's an X value you want to check? 0, okay? So let's check 0. So I'm going to find f of 0. That means I'm going to take my function, 3 to the x. I'm going to plug in 0 there. So that's 3 to the 0 power. And what should 3 to the 0 power give us? Good. Anything to the 0 power should be equal to 1, right? So that tells us the y value here is going to be 1. What other x values do you want to check? Okay, positive 1. So if I do f of 1, it's going to be 3 to the first power now. And what should that give us? 3. Good. So there we go. Let's get a few more values here. So what other values do you want to check? 2 works. We'll do f of 2. That's 3 to the second power, which would give us what? Good. 3 squared is 9. So there's our y value for that one. All right, so let's go the other direction now, right? So what other values could we choose on the other side then? Okay, so let's go with negative 1. So f of negative 1, 3 to the negative 1 power. So what's that going to give us? Yeah, 0.3 repeating, which is the same thing as what? 1/3, right? And remember, our for exponents, whenever you have a negative, we can always move it to the denominator. So this is just going to become 1/3 to the positive 1 power, and that's how we get 1/3 this time. There's our value for negative 1. Let's do one more negative, so I'll go with negative 2 here. So f of negative 2, what should 3 to the negative 2 be equal to? One over 9, good, right? Because again, it's going to become 1/3 squared. 3 squared is 9, so we just get 1/9 as that value. Okay, so let's start here, right? So we got 5 points that we can plot. Let's see if that gives us a decent idea of what this graph's going to look like. So our first point we've got is at 0, 1. So we have an x value of 0, meaning we're not moving left or right, and then the y value is 1, so we're going to go up 1 on the y-axis. Now we've got this point right here. So that is our y-intercept. Now on 3, we're going to go right 1. We're going to go up 3. It's going to put us right here. Now, to 9, I'm going to run out of space here, right? But I want to go up 9, which is going to put us way up here somewhere. So if I go over 2, just know that this point's going to be way up here, okay? Now my negative values, I want to go negative 1 to 1 and then up 1/3. So if I go left 1 and up 1/3, I'm only going 1/3 of the way to 1, so that's going to put me right down here. Now when I get to negative 2, now I'm at 1/9, which is smaller, right? So I'm even closer to the x-axis there. So really, really small values this time, and that's what we get. So now here's the question. As I go out to the right, what's happening to my graph? What value am I going to be approaching over here to the right-hand side? Infinity, right? So this side of my graph is going to grow really, really fast, right? And it's going to shoot up towards positive infinity on that side. Now, as I go to the left, what's going to happen to my graph? It approaches 0. Good. It's never actually going to get to the x-axis, right? It's not going to cross the x-axis because no matter what values I put over here, these fractions just get smaller and smaller and smaller, but they're never actually going to become 0. They're definitely never going to become negative. So what's happening is this graph approaches the x-axis. It approaches a y value of 0, but it's never actually going to get there. So we have this graph that does this, curves up, and it's just going to continue out that direction like that. Okay. Good, right? So there is no restriction on the x, right? I can put any x value I want to in there. So if we're looking at domain this time, the domain is all real numbers, negative infinity to positive infinity for the x. Now the range of this graph goes from what to what? Good, 0 to infinity, right? So in terms of domain, not that we were asked to find it, but just to kind of talk about it, that was all real numbers. But the range this time starts from 0, not including 0, and it goes all the way to positive infinity, right? Because here's my 0, and then up to positive infinity. Now, the general name we give that graph, this right here is what we call a J-shaped curve. Okay. Whenever you see a graph that looks like that, where it's growing exponentially towards infinity to the right, we call that J-shaped because it looks like the letter J. Any questions on that graph? All right, let's look at the next one now. So now we've got 1/3 to the x power, right? So again, I'm going to do the same thing we did last time. I'm going to create a table of values. Okay, and let's go with these same x values that we chose before. So 0, 1, 2, -1, -2. Right, so this time, if I do f of 0, and I'm using my 1/3 to the x, give us 1/3 to the 0 power. Well, what's 1/3 to the 0 power going to be? Still 1, right? Anything to the 0 power should always be equal to 1. So we're still going to have a point at 0, 1 this time. Now I'm going to do f of 1. We've got 1/3 to the first power. What should that give us? Good, 1/3. All right. We do f of 2. What will 1/3 squared give us? Okay, sorry. Let me know if it gets any worse or better or anything like that. But yeah, at least try to follow along with the video and the work here. All right, good. So this will give us 1/9. Because remember, we can square the 1, we can square the 3, and that's going to be 1/9. So this value here, 1/9. Then we're going to do -1. So what will 1/3 to the negative power give us? Because remember, again, when we have a negative exponent, if we have a fraction in here, we can just flip it and then raise it to the positive power. So this becomes 3/1 to the 1, which is just positive 3 now. And then finally, f of -2. We can use that same rule. And so once we flip it and we square it, that becomes 9. Good. All right. So now, what do we notice about those values? They're flipped. Good, right? So they're the same values we got in the first one, except now we got the fractions for the positive values and we got the whole numbers for the negative values, whereas up here it was reversed, right? So let's think about what that's going to look like when we actually graph it then. So we still have that point at 0, 1. This point right here has not changed. But now when we go to 1, that value is 1/3, right? So it's going to be down here. And when we go over to 2, that value becomes 1/9. So again, we're getting really small, really close to 0 now. And now on the other side of our graph, -1, we're going to go up to 3. And again, the -2, that's going to be all the way up here somewhere, right? So all the way up at +9. So if we connect this now, we're going to get something that looks like this. Now, since we did domain and range on the last one, let's do the same thing here just to kind of compare the two graphs. What's the domain for this graph that we've got now? Good, right? So again, this is still going to be all real numbers. There are no restrictions on my x, so -infinity to +infinity. What about the range of this graph? Good, right? So just like before, we don't have any values below the x-axis, so 0 is the smallest value, and we're never going to actually get there, so we don't want to include 0, but then it is still going up towards +infinity in terms of the y values here. So everything's positive, so 0 to infinity. Now, this graph up here was what we call a J-shaped curve, right? Because it looks like the letter J. This curve down here is going to be what we call an L-shaped curve. And again, it's because it kind of looks like the letter L when it goes this direction. Now, how are those two graphs related to each other? So if I just asked you to compare the two graphs, what could you say about them? Okay, so they're either exponential growth or exponential decrease, right? And we'll call that decay later on, but that's right. Okay, so one's exponential growth when it grows like this, the other is what we call exponential decay when it goes down like that. All right, good. So Naomi says it's a transformation, right? So thinking about this graph would just be a transformation, and Kenneth, this guy, is just basically flipping it over the y-axis, right? So we basically have a reflection here. If we were to take this graph and just reflect it over the y-axis, it would actually give us this graph right here. So what that tells us is that this graph right here is really just 3 to the negative x power. Because if I were to put a negative in front of my x right here, that would give us a reflection over the y. And this right here, if I flip this and make that a positive exponent, would actually become this function here. Okay, so not essential, right? But just so you kind of understand, the reason these are just reflections over the y-axis is because I could rewrite them down here as 3 to the negative x, which gives us that reflection over the y-axis now. Any questions on those? Now, the next slide just kind of puts all this together and explains why it's important that we recognize what the base is and what the graphs are going to look like. Okay, so if we have our exponential function, a to the x, anytime that a value is greater than 1, right? So as long as we have a value that's greater than 1, we're going to have this J-shaped curve that we have right here. If we have an a value that's a fraction or decimal between 0 and 1, that's when we're going to end up with that L-shaped curve instead. So think about the last example. We had 3 that was greater than 1, that gave us a J shape. When we had the 1/3 that was between 0 and 1, that gave us the L-shaped graph. Notice both of these graphs are going to go through the point 0, 1, right? So that's going to kind of be our starting point regardless. Okay, but bigger than 1, J shape, between 0 and 1, L shape. And then we'll look at transformations from those basic graphs, right? But those are the 2 basic graphs we're going to start from, and then we'll apply some transformations to those. Any questions there? Again, I'm not going to spend a ton of time on that because you can go back and look at it if you need to. Let's look at these graphs now. So this time they're giving us the graphs. They want us to find the function. All right, so if we look at this first one, we know we're trying to get a function of the form a to the x power. And this time they actually give us a point that's on our graph. So what do you think we might be able to do this time if I'm trying to find this function given that point right there? Okay, so the table in this case is not going to necessarily help us too much because we don't have a ton of information, right? Basically, we know, well, it goes through this point here, which looks like 0, 1, and then it looks like it goes through this point here, but that's really all we have, right? It's just those 2 points. So what we want to figure out is just given really this information here, how could we actually figure out what the equation is going to be to give us this curve? Tell me this. What information do we know just based off of that point? What does a point give us? Good. We have an x value, and we also have what? Okay. So be careful, right? We're not going to find slope because it's not a line, right? So we can't just use slope in this case because it is a curve, right? And that slope will vary as we go. So German says y equals a to the 2.2. Okay, be careful. This is a comma, right? So this is 2 comma 25. So this is actually x and y time. Okay. All right. So Anthony says it should be 5 to the x. That is correct. Okay. So Anthony, can you explain how you got that? Good. All right. So 5 squared is 25. So the way I'm going to do this, f of x is just y, right? So this is my y value. So I'm going to put that in place of my f of x. So that's going to give me 25 equals. I'm looking for my base now. So I need to know what a is. But I have the x value this time, which is the 2. Right? So we know that 25 should be equal to a to the second power. Well, now I just need to know what is this base right here. Well, how can I find a at that point? Square root, right? So all I want to do here is just take the square root of both sides. That's going to give me my a value. And what's the square root of 25? 5, right? And we know this needs to be a positive value because we said in general, right, all of our bases are going to be positive anyway, but that's what's going to give us that J-shaped curve is the positive value. So we don't need a plus or minus or anything like that. So it's just going to be positive 5. So our f of x this time is equal to 5 to the x power. That's going to be the function that would give us that graph. Any questions on that one? All right, so how are we going to set up the next one then? So this time we point at 3/1/8. Okay, so as well, you're on the right track, right? So it's going to be the 1/8 is the y value. So we're going to start with that. And that should be equal to a to the what power this time? 3. Good, right? Because again, the x value this time is our exponent. This x value is 3. So I'm just going to put a 3 right here this time. Okay, now how would you solve that one to find a value? Good. This time we're going to have to take the cubed root of both sides to get rid of the third power. That gives me my a now. What would be the cubed root of 1/8? Good. So the cube root of 1 is 1. Cube root of 8 is 2. We just end up with 1/2 in this case. So what's the function going to be this time? Good. So it's just going to be 1/2 to the x power. So anytime you're given something like that where you're looking for the function itself, right? Plugging your y, plugging your x, solve for a. Once you know a, that gives you your base, and so it's just going to be that base to the x power. And in this case, right, we have an L-shaped curve, so that tells us that our base should be somewhere between 0 and 1. So getting a value of 1/2 makes sense this time. Any questions on that one now? All right. So now let's look at some transformations. So we're going to start with a parent function of 2 to the x, and then we're going to think about what transformations we're applying to each one of those graphs. And then we'll talk about domain, range, and asymptotes. All right, so first off, let's just think about what does that parent function actually look like. Okay, so if we start with the 2 to the x, what's the graph of 2 to the x going to look like? J-shaped curve, good, because the base is bigger than 1. It's going to have to go through what point? Good. All right, so it's going to have a y-intercept at 1, and it's going to be a J-shaped curve. So it's going to look something like this right here. Again, this is just a rough sketch, right? So it doesn't have to be perfect. Okay, but as long as you kind of start from there, that's our parent graph. That's the one we're going to be transforming now. So now let's look at g of x. So if we look at this function here now, what type of transformation are we going to have? Good. So this is going to give us a shift up 1 unit, right? So now let's think about our parent function, right? And let's think about shifting that whole thing up 1. It's going to be g of x. So what's going to change about that graph then if I shift everything up 1 unit? Okay, good. The y-intercept is going to change. So now instead of being at 1, the new y-intercept is going to be 2. Good, because that's going to get shifted up 1 unit. Now we have a new y-intercept at 2. What else is going to change about that graph? The range, right? Because now if I take this graph and I shift everything up 1 unit, instead of this horizontal asymptote along the x-axis like we did before, where is that horizontal asymptote going to be now? It's going to be at 1, right? So now we're going to have, drawing a dotted line here to represent the horizontal asymptote. That horizontal asymptote gets shifted up, and so we still have a J-shaped curve because it's still 2 to the x, but now it's going to go through the point 0, 2, and our horizontal asymptote this time is going to be at 1 instead. So now we have horizontal asymptote, y equals 1. Now let's talk about domain and range. Okay, so what would be the domain for that new function? Good. So it's still going to be all real numbers, right? Because I can still put any x value I want to in there, still going from negative infinity all the way to positive infinity, left to right. What about the range this time? Good. So this time we're starting from 1 and going to infinity because that horizontal asymptote now got shifted up to positive 1. So that's going to be our lowest y value, and then it's going to go up towards infinity this time. Any questions about any of those pieces once we do that transformation now? All right. Let's look at h of x. So what type of transformation are we going to have this time? Okay, good. So this is going to give us a reflection, and because the negative is out front, that's a reflection over the x-axis. Let's think about this graph. And so again, we're going back to our parent function now, and if I reflect that over the x-axis, what's going to change? Okay, so is the horizontal asymptote going to change if I just reflect over the x-axis? So remember, over here now, we're approaching 0. If I reflect that over the x-axis, what am I still going to be approaching? Yeah, right, it's still approaching the x-axis just from the bottom instead of the top. Right, so the horizontal asymptote's actually going to stay the same. So what is the horizontal asymptote for this graph? So this is just going to still be y equals 0, because again, it's still going to be approaching 0 just from the bottom. What is something that would change? Y-intercept, right? So instead of being up at +1, it gets reflected over the x-axis, so now it's down here at -1 instead. We already said our horizontal asymptote's still at y equals 0, so now our graph is going to do something like this instead. So any questions on that reflection? All right, now Kenneth, you said vertical asymptote. Tell me this, do we have any vertical asymptotes for the parent function? Okay, good. So the y-intercept would change, right? So just keep in mind here, with all of these exponential functions, we should not have any vertical asymptotes because our domain is always going to be all real numbers, so long as we don't put any weird stuff in there, right? But in general, all of these exponential functions should be all real numbers. All right, so now let's talk about domain and range for this one. So what is the domain for my new transformation line? Good. Negative infinity to positive infinity. And what's the range going to be this time? Good. Except remember, we always want to start smallest to largest. So the negative infinity would come first. And it's going to go up to 0, right? Because we got from negative infinity up to 0. That's going to be our range here. Any questions on any of those pieces now? All right. So we get this k of x function now. So what are we doing to that one? What kind of transformation do we have this time? Good. So we have a shift to the right 1 unit. Because this time the -1 is with the x in the exponent, right? And remember, this is always opposite of what you would expect. So a -1 actually shifts it to the right 1 unit. Let's think about that graph then. So again, go back to your parent function. If I shift that graph to the right 1 unit, what's going to change? Good. The y-intercept is going to change, right? So think about it here. If I take this y-intercept, we have a point at 0, 1. I'm going to shift that point over to the right. So what's going to happen is I'm actually going to have a point now at 1, 1 instead of 0, 1. So I'm shifting that y-intercept over to the right one. Well, that means it's going to also change where the y-intercept actually is here. Now, I don't really care if you know exactly what the value is. We could go back and find it if you want to. Is the horizontal asymptote going to change? No, right? Okay, because if I just take this graph and I shift it to the right, I'm still going to be approaching 0 along the x-axis there, right? So this thing's going to be right here. It's going to have to cross somewhere below 1 so that it can go through the point 1, 1, but then it's going to continue up towards positive infinity because it's still going to be that J-shaped curve because the base is 2 here. So like we said, horizontal asymptote should still be y equals 0. That's not going to change. Now let's look at our domain range. So what's the domain going to be this time? Okay, good. That hasn't changed, still all real numbers. And what's the range going to be? Good. So just like the parent function, it's going to be 0 to infinity because I still have that horizontal asymptote at 0. Just shifting it left or right is not going to affect that. Okay, so my range is still 0 to infinity, just like the parent function for that one. Any questions on that one now? Now, if you really wanted to know what the y-intercept would be for that last graph, how would you find the y-intercept? Plug in 0 for x, right? And so if we put a 0 in place of x here, that gives us 0 minus 1. Well, that's a negative 1. What would 2 to the negative 1 power be? 1/2, right? And so that tells us now that our y-intercept should be at exactly 1/2, halfway between 0 and 1 this time. So if you really wanted to know, but again, as long as you know the transformation, you know that point's going to move over 1. That means it's going to be somewhere lower than 1 when we cross over the y-axis. That's all that really matters. But you could plug in 0 and find the exact value there. Anybody need more time on that one? All right. Not doing that one. All right, so I'm going to let you go ahead and get this formula written down because I do think it's important. We'll discuss the pieces, and then we'll probably wait till Monday to actually do an example with it. Okay, but this is what we call a compound interest formula. It's one of our main applications of exponential functions. Okay, so go ahead and get this down, and we'll talk about all these pieces, and then it'll probably be time to go by the time we do that. All right, so I'm going to go ahead and start talking about each of the variables now. So A of t, amount after t years, that's basically your total, right? So that, I think, is kind of self-explanatory, right? So after a certain amount of time, that's the amount we're going to have. Now, principal, does anybody know me by principal? Original, right? And so I'm going to call this the starting amount. So your principal is always however much you start with, right? So that's your starting point. Now, the interest rate typically is going to be given as a percentage. We just have to make sure when we put it into our formula, we want to make sure we convert it to a decimal, okay? So that's the one thing we have to keep in mind there is when they give you the interest rate as a percent, just make sure you convert it to a decimal before we actually put it into the formula. Now, the n is the number of interest, the times the interest is compounded per year, okay? And we'll get that from a keyword within the problem. And then t is just number of years, okay? So again, that's self-explanatory. Now let's talk about real quick our n values and what they actually mean. Okay. Or I'll say keyword here. So does anybody know any keywords that you might see in one of these interest problems that would give you an N value. Annually, good. Okay, so one of our words here is going to be annually. That would mean it's compounding. Annually would be how many times per year? Once, right? So that'll be an N value of 1. All right, so semi-annually. We'll spend some time going through these again next week too. That would be twice per year, so our N value would be 2. Quarterly would be how many times per year? 4 times per year. Right. Any other keywords you might see? I know we're out of time. I just want to get all these down real quick. Okay, so another one you might see is monthly. So if we compound monthly, how many times per year would that be? 12 times per year, right? And then the last one, that's one that we see a lot, would be daily. So how many times per year would daily be? Good. So we're always going to use 365. We ignore leap years there. Okay, so daily would be 365. So I think those are probably the only ones you would see. You know, bi-monthly, bi-weekly aren't as common. You could see them, but these are the ones I would say that you really need to know. So as long as you recognize those words and the N values that correspond to those words, that's the main thing. But again, we'll review those on Monday, and then we'll do an actual example with that. So that's all I've got. Good weekend. Again, let me know if you're having questions or concerns as you're working on the test or trying to upload it. I will see you guys on Monday.